I want to start today by asking you to picture the absolute coldest place you can imagine.
Yeah.
Maybe it's deep space, between the galaxies. Maybe it's inside one of those cryo chambers in a high-tech lab. We have this very specific mental image of what ultimate cold feels like, right?
Sure. Stillness, silence, everything just locked in place.
Exactly. And that's what we're taught in high school, maybe even middle school. We learn that heat is basically just motion. It's atoms jiggling around. So logically, if you take that to its limit, absolute zero Kelvin or minus 273.15 Celsius is the red light,
The cosmic stop sign.
the point where the universe just
Well,
freezes.
as the standard textbook definition, it's often called the billiard ball model. If temperature is just speed, then zero temperature must mean zero speed.
But here's the thing that has been bothering me since I started reading this paper you sent over, and I really want to push on this because it feels like a massive plot hole in physics.
Go for it.
If absolute zero means zero motion, then the universe shouldn't exist. Well, think about it. We know that even at absolute zero, electrons are still zooming around the nucleus of an atom. Protons and neutrons are spinning inside the nucleus. I mean, quantum mechanics says you can never pin a particle down completely.
Right.
So if motion actually stopped, wouldn't the atom just collapse? Wouldn't matter, just cease to be matter.
It would. If all motion truly ceased, the structure of the atom would fail.
Mhm.
And that is the exact paradox we are dealing with today. We are looking at a paper by Jerry Z. Liu titled The Nature of Absolute Zero Temperature.
And it's a big deal.
Oh, yeah. And honestly, calling it a correction is too mild.
Yeah.
This is like a rewrite of the source code.
It feels like we're debugging a glitch in the matrix.
It is. Because the paper argues that our entire definition of temperature, the one we use to design engines, study stars, understand the climate, is missing two-thirds of the picture.
Wow.
We've been obsessing over speed and ignoring the real drivers of heat.
Okay, so the mission today is to figure out what temperature actually is, if it's not just speed. And I know we're going to get into this new framework called dynamic energy, which sounds very sci-fi.
It does this.
But before we get to the solution, I want to understand how we got it so wrong in the first place. Who decided cold equals stillness? Why is that the default setting in our brains?
Well, you have to go back to the 1600s, Robert Boyle, and later the visualization of Charles's law. Imagine a graph.
Okay.
On the y-axis, you have the volume of a gas, how much space it takes up. On the x-axis, you have temperature.
Okay, I'm visualizing. I take a balloon, I cool it down, it shrinks.
Right. The line on the graph goes down. As the temperature drops, the volume drops. Now, if you take a ruler and extend that line all the way down until the volume hits zero.
Meaning the gas theoretically vanishes into nothingness?
Exactly. That line hits the x-axis at exactly netical 273.15 degrees Celsius.
So absolute zero is basically a mathematical projection. It's where the math says the gas should disappear.
Theoretically, yes. It's an extrapolation. And that led to the third law of thermodynamics. The standard version says that at absolute zero, a system is at minimum possible energy.
Right.
And since everyone at the time assumed energy meant motion kinetic energy, they assumed it meant minimum motion.
But hold on, you're saying minimum energy and zero motion aren't the same thing.
Not at all. Not even close. And this is where the standard model starts to crack. The paper gives a brilliant example to prove it.
Okay.
Imagine a crystal made of radioactive material. We cool it down to absolute zero. According to the motion theory, it's dead. Frozen.
It's sitting there shivering at 0 Kelvin.
But it's radioactive. Suddenly, a nucleus inside that crystal decays. It spits out a particle. There's a massive release of energy. The temperature spikes immediately.
But wait, the crystal was frozen? It was supposed to be at the finish line.
Exactly. It's supposed to be at minimum energy. But clearly it wasn't. There was energy locked deep inside the structure, nuclear potential energy,
Yeah.
that had nothing to do with how fast the atoms were wiggling.
So it's like saying a car has zero energy just because it's parked in the driveway, even if the trunk is full of dynamite.
That is the perfect analogy. The motion theory of temperature only looks at the speedometer. It ignores the explosives in the trunk, it ignores the battery charge, it ignores the fuel in the tank.
Okay, so we know the billiard ball model atoms just bouncing around is incomplete because it ignores all the internal stuff.
Right.
But the part of the paper that really broke my brain, and I need you to walk me through this, was the thought experiment with the vacuum. This feels like a riddle.
It's my favorite part of the paper because it's so simple, yet it completely dismantles the standard definition. It's figure 3 in the text.
Okay.
I want you to imagine a glass bulb that has been completely evacuated, a perfect vacuum.
Empty space. No air, no atoms floating around.
Suspended in the middle of that bulb, catching nothing, maybe hanging by a non-conductive thread, is a standard thermometer.
Okay.
Now, play devil's advocate for a second. Standard physics says temperature is the average kinetic energy of particles colliding with a thermometer.
Right.
Air molecules hit the glass, transfer energy, mercury rises. That's the mechanism, right?
Right. Mosh pit physics. You need bodies hitting bodies to transfer the shove.
But in this bulb, there are no bodies. There is no air, no collisions.
So, logically, the thermometer shouldn't read anything. It should be isolated from the universe.
If the standard theory were 100% true, yes. But we know from experience that if you shine a flashlight on that bulb, the thermometer rises.
Right.
If you put the bulb in a freezer, the reading drops.
But nothing is touching it. How does the thermometer know it's in a freezer if there's no air to tell it?
Radiation,
Ah.
waves, light, infrared. Even in a vacuum, energy is crossing that gap.
So temperature isn't just about being hit by atoms, it's about absorbing light.
Precisely. The thermometer's reading the radiative environment.
Yeah.
And this leads us to the author's new framework. He says we need to stop using vague terms like thermal energy or just saying it's heat. We need a precise equation.
Yeah.
He calls it dynamic energy.
Okay, let's unpack this. The paper gives a formula. D equals U plus K plus R. I usually hate alphabet soup, but this seems important.
It is.
We know K is kinetic, that's the motion we've been talking about. And R is what we just found in the vacuum radiative energy.
Correct. So we have motion K and light R.
But the big one, the one we've been ignoring, the one that explains the radioactive crystal, is U, potential energy. Where is that hiding?
In the bonds, in the tension. Think of an atom not as a hard ball, but as a system of springs and orbits. Electrons are orbiting the nucleus like satellites. Chemical bonds are holding atoms together like stretched rubber bands.
So U is the energy stored in the rubber bands.
Yes. And the author argues that true temperature dynamic energy is the sum of all three. It's the motion K, the radiation R, and the tension.
This explains the radioactive crystal perfectly. It had zero motion, maybe zero radiation, but it had massive potential energy. The springs were coiled tight.
Exactly. And the most fascinating part is that these three aren't static. They're constantly shape-shifting into each other. The paper calls it the triangle of energy transformation.
Shape-shifting how? I get how a spring can snap and cause motion, but how does this happen at the atomic level? Like, how does tension turn into motion?
So the paper introduces a mechanism for this called transimpact.
Transimpact. Sounds like a sci-fi movie. Or a transformer.
It kind of does. It describes something very violent happening at the atomic level. We tend to think of atoms just, drifting around. But imagine an atom absorbs some energy. Maybe a photon hits it.
Okay.
An electron gets excited and jumps to a higher orbit.
It moves further out from the nucleus?
Right. The electron cloud expands, but it doesn't just drift out. It pops.
Pops.
Like popcorn.
Okay, I like that visual. Atomic popcorn.
That expansion is sudden. It elbows the neighboring atoms out of the way. That shove, that expansion is potential energy, the electron moving out, turning into kinetic energy, the neighbor getting pushed. The pop is the motion.
So things move because they're expanding into each other.
Yes. This suggests that Brownian motion, that random jittering of particles we see under microscopes, isn't just mysterious jiggling. It's a series of tiny explosions. Transimpact.
That makes the atomic world sound a lot more chaotic.
Oui.
But things don't speed up forever. Eventually they slow down. You rub your hands together, they get warm. Motion turns into heat.
And that is the reverse process. The paper calls it impact trans.
Impact trans. Okay, break that down.
When you rub your hands, the molecules in your skin are colliding. That collision, the kinetic energy, hammers the electron clouds of the atoms in your skin.
It shakes them up.
It disturbs them. It knocks the electrons around. And to stabilize, those electrons have to release that excess energy.
So they emit photons.
They radiate infrared waves.
Which I feel is warmth.
Exactly. Motion, kinetic, hits the atom, and the atom screams out light, radiative. That's impact trans.
It's a constant loop. Popcorn expansions create motion. Collisions turn motion back into light or stored tension. It's like a currency exchange that never closes.
Pretty much.
But there's a huge caveat here I want to address. We're talking about dynamic energy, the active stuff. But what about the mass itself? We haven't talked about Einstein yet.
The heavy hitter, E equals mc squared. The paper classifies this as matter energy, or M.
How is matter energy different from the dynamic energy we just talked about? Because mass is energy, right?
It is, but think of matter energy as The money in a long-term savings account that you can't touch.
Oh, okay.
Dynamic energy is the cash in your wallet that you spend every day. Most of the energy in the universe is locked up in mass. It's the M. It's stable. It doesn't affect the thermometer.
Wait, really? The mass doesn't affect the temperature?
Not directly.
Mhm.
And the paper compares Jupiter and the Sun to prove this. This is a great comparison.
Okay.
Chemically, they're almost identical. Both are giant balls of hydrogen and helium.
But the sun is significantly hotter. Just a bit.
Right. But why? They have the same mass composition.
Mm.
The difference is that Jupiter's energy is locked in the vault.
Mm-hmm.
It's stable. The hydrogen's just sitting there. The Sun, however, has cracked the safe. It is performing nuclear fusion, converting that locked matter energy into dynamic energy radiation and kinetic motion.
So the sun is burning its savings, Jupiter is hoarding it.
Perfect. Temperature measures the burning, not the hoarding. A thermometer measures activity, not net worth.
That helps distinguish the two. So if we go back to our original goal redefining absolute zero, it's not enough to just stop the car. Zero motion isn't enough.
No, that's the old definition. To reach true absolute zero, you have to drain the entire system.
Oh.
1, you need zero radiation. R equals 0, no glow. 2, you need zero kinetic motion. K equals 0, no vibration.
Okay.
And, this is the missing piece, you need minimum potential energy. The electrons must be in the lowest possible orbits. The bonds must be completely relaxed.
Used to quiet the springs inside the atom, not just the atom itself.
Correct. And even then, as we saw with the radioactive crystal, if there is nuclear potential energy waiting to decay, you can never be truly at zero energy. But you can minimize the dynamic components.
This new definition seems rigorous. It covers the holes. But I play the skeptic for a living. Does this actually solve real-world problems? Or is this just semantics?
Oh, it solves problems.
Because there was a section in the paper about specific heat and the octane error that seemed to suggest our current math isn't just slightly off, but drastically wrong.
Yeah, it's drastically wrong.
Mm-hmm.
This is the smoking gun for me. If you're listening and wondering, does this actually matter? Yeah. This is the part where you pay attention.
Okay.
There is a standard model called the kinetic theory of gases. It predicts how much heat a substance can hold based only on the idea that particles are bouncing balls.
It assumes the energy is all in the bouncing. It ignores the bond.
Completely. Now, for simple gases like helium, which is just a single atom, this works. The prediction is 99% accurate.
Because helium doesn't have complex bonds, it is just a bouncing ball, so the theory gets lucky.
Exactly. But then you try to predict the heat capacity of octane, gasoline. A long, complex chain of carbon and hydrogen.
It has bonds everywhere.
It's a spaghetti monster of potential energy. The standard kinetic theory predicts a number for how much heat octane can hold. And when you measure it in the lab, the prediction is off by 93%.
Whoa, wait. 93%? That's not an error margin, that's a hallucination.
It predicts only about 7% of the actual heat capacity. Imagine you're designing an engine or cooling system for a rocket, and your thermal calculations are off by a factor of 14.
That's catastrophic.
It is.
So where was the missing 93% of the energy hiding? If it wasn't in the motion, where was it?
In the bonds, in the
Wow.
potential energy. The standard theory couldn't see it because it was only looking for motion, but the energy was being soaked up by the bonds stretching and wiggling.
So what happened when the author looked at it?
When Jerry Liu, the author, plotted the specific heat against the number of bonds in the molecule,
Let me guess. It worked.
a 98% match.
Wow.
This proves undeniably that potential energy, the bonds, is the dominant factor in heat capacity for complex molecules, not the speed of the particles.
That is the mic drop moment. You can't ignore the bonds. You know, this actually completely changes how I view boiling water, too.
Oh, yeah.
We've all learned that phase transition paradox, right? You heat water to 100 degrees, it boils. You keep adding fire. The fire is hot, but the water stays at 100 degrees.
It flat lines.
If temperature is speed, why aren't the molecules speeding up? I'm paying for the gas bill, I'm adding energy.
Because the energy isn't going into speed, it's going into structural demolition.
Structural demolition, I like that.
Think about it. Liquid water is held together by bonds. To turn it into gas, you have to break those bonds. The input energy is being swallowed by potential energy. It's doing the work of snapping the rubber bands.
Right.
Since the dynamic energy level, which we read as temperature, is anchored to the state of those bonds, the temperature cannot rise until the bonds are broken.
It's like paying a toll. You can't speed up on the highway until you pay the toll to break the bond.
Exactly. The energy is rerouting from temperature to phase change. The kinetic theory struggles to explain this intuitively, but the dynamic energy model makes it obvious. You were filling the potential energy bucket, not the kinetic energy bucket.
It's a lot to process. We've moved from temperature is jiggling to temperature is a complex interplay of radiation, bond tension, and explosive expansion.
It's a big shift.
Why does this shift in perspective matter to the person listening right now, aside from winning arguments with physics teachers?
It matters because we are reaching the limits of what the old model can do. We are designing materials for quantum computing, for fusion reactors, for interstellar space travel. In those extreme environments, super cold or super hot, you cannot ignore the bonds. You cannot ignore the radiation. If you treat a complex plasma like a simple billiard ball gas, your math will be wrong. Just like with the octane, we need the full picture to build the next generation of technology.
It's a reality check. We need to trust what our instruments are telling us. You know, I was thinking about this during the break. We measure the temperature of stars billions of miles away.
We do.
We can't touch them. We can't put a thermometer in them. We definitely can't measure how fast their atoms are moving. All we have is their light.
Wien's law, the color of the light tells us the temperature.
Right. So we aren't measuring a collision. We are analyzing a song. We are listening to the frequency of the electron bonds stretching and relapsing and emitting waves.
That is a beautiful way to put it. The universe is vibrating, not just colliding.
It makes you wonder, if we stopped thinking of the world as a car crash of atoms and started thinking of it as a symphony of energy states, what else might we discover?
I think we'd find that the universe is a lot more connected and a lot more dynamic than we ever thought.
A symphony of bonds. We'll leave you to vibrate on that thought. Thanks for taking the plunge with us today.
Always a pleasure.
We'll see you on the next deep dive.